Hello, calculus students. We're going to continue working with volume today. This time it's going to be working with volumes of solids of revolution. So I'm going to share my screen here and start the presentation. So hopefully you have your notes out in front of you. Let's go back here. Looks like we got all the stuff from the old lesson. All right, so first we're going to look at what's called the disk method. The reason it's called a disk is if I take some axis, here's my axis, and here's a curve. If I take my representative rectangle and I rotate it around that curve, the shape that is formed when I spin that all the way around is a disk. It kind of looks like a circle. All right, so we call that the disk method. This thing, if we think about it, when I'm rotating that shape, let me grab my pen. Oh, go back, please. So I have my graph. Let's try that again. I have my graph. I have some curve. I have a representative rectangle here. When this representative rectangle gets rotated, let's say I'm rotating around the axis, that shape that's formed when it spins all the way around, here's like a little side view, is a circle. And the height of the curve here, this representative rectangle, is the radius of the circle. And we know that to find the area of a circle, it's pi times radius squared, which is where this formula comes from for the disk method. We have pi, and the radius is this representative rectangle's height. So that's our r, pi r squared. And when we do infinitely many of those little representative rectangles, or disks as we have them, when we do an integral from a to b, it will fill in all the gaps here of all these representative rectangles, and the resulting thing will be a solid. All right, that's why it's a solid of revolution. We're rotating it or revolving it around an axis. We can have a horizontal axis of revolution or a vertical axis of revolution. When it's vertical, we just change all our components to y's instead of x's. So let's take a look at an example. This first one we have, find the volume of the solid formed by revolving the region bounded by the graph of y equals 4 minus x squared in the x-axis from 0 to 2 about the x-axis. So you have this example in your notes, and we actually did a problem similar to this. Looks, I think, just one lesson ago. We're going from 0 to 2. So our curve here is a parabola that's 4 units up. Normally there'd be another half here, but we're only looking at this half here that goes from 0 to 2. So this is our shape that we are going to revolve around the axis, and we're going around the x-axis. I'm going to grab a different color here. This is my representative rectangle here, the height of this curve. That's my big R. That's how tall it is. I am rotating R around the x-axis. So we're going to have an integral that goes from, well, first of all, let's write down our pi and its volume. So we have pi times the integral from 0 to 2. Our big R here, the height of this representative rectangle, is this curve. That's our big R, 4 minus x squared. So we have pi times big R squared. And remember, the width of our representative rectangle is delta x, which we show in the integral as dx. All right, that will find the volume using the disk method of this curve revolving around the axis. This shape, I think, kind of, if you want to picture what it would look like, it'd be like if you, I don't know, split an M&M down the middle. When we rotate it, it'd be kind of a, I don't know, like half an M&M shape that's going to result. If we had both sides, it'd probably be more M&M shaped, right? But it's kind of split along its equator. All right, so let's find this volume. I'm going to have to FOIL that all out. We had this, I think we had the same curve before. So 4 squared is 16. 4 times negative x squared plus another one of those would be negative 8x squared. And x squared is x to the 4th dx. All right, we're going to find the antiderivative of that. Don't forget to multiply by pi. That's something that tends to be left out when students do these. So 16x is the antiderivative of 16 minus, this would be 8/3 x cubed. Antiderivative of x to the 4th, 1/5 x to the 5th. And we are evaluating from 0 to 2. So I'm going to plug a 2 in everywhere and then my 0. So plugging in 2, I have 16 times 2 is 32. Minus 2 cubed is 8 times 8 is 64/3. 2 to the 5th is 32 fifths. And when we plug in 0, we're going to have minus 0, because if I evaluate all of these at 0, I'm just going to get a 0. So I simplify that, and I'm going to end up with, let's see here, we have, if we get common denominators here, looks like this is 480/15 minus 320/15 plus 3 would be 96/15. So altogether, our final answer is 256/15 pi. All right, and that's the disk method. So you have pi times your big R, right? Your big R is the representative rectangle squared, right? The height of the curve, dx. Let's look at another one. So this time it says find the volume of the solid form by revolving the region bounded by f of x equals 2x squared and g of x equals 8 about the line y equals 8. So this one is different because our axis of revolution is not the x-axis or the y-axis. It's a line somewhere else. So I have 2x squared. And I have the line y equals 8. I'm just going to draw it in here. And we are taking this shape. We're taking this whole thing. Right? I'm going to switch color here. I'm going to draw in my representative rectangle. This time I'll put it over here. Remember, it doesn't really matter where it is. So here's my representative rectangle. It's the height here, which actually is the difference between these two curves. This is my big R. And I'm taking that representative rectangle and rotating it around the line y equals 8. All right, so another thing I'm going to need to know here, notice they didn't give me my limits of integration, so I need to figure those out. So I'm going to take 2x squared, set it equal to 8. I divide both sides by 2, and I get x squared is equal to 4. So x equals plus or minus 2. Those are my limits of integration. I have that my volume will be equal to pi times the integral from -2 to 2. Now let's talk about what our big R is here. You did this a couple lessons ago. The height of this is the difference between these two curves, right? If I go all the way up to the top, that'd be 8. If I do here to the curve, that would be 2x squared. So the height of the representative rectangle is 8 minus that 2x squared. So my big R in this case is equal to 8 minus 2x squared. That's the height of the rectangle, is the difference between those two curves. So I have 8 minus 2x squared squared. Pi times the radius squared, pi r squared squared dx. Right? Again, you may have noticed that this is also an even function, right? It's symmetric about the y-axis. So I could, instead of doing my limits of integration from -2 to 2, I can multiply by 2 on the outside, right? Just make it double from 0 to 2. I'm going to go ahead and multiply all of this inside part out at this point. So 8 squared is 64. 8 times 2 is 16. 16 and 16 would be 32x squared plus 4x to the 4th. All right, find the antiderivative. I get that the volume is 2 pi times 64x minus 32 thirds would be the antiderivative here, 32 thirds x cubed. Antiderivative 4x to the 4th would be plus 4/5 x to the 5th. And we are evaluating that from 0 to 2. All right, so I'm going to plug my 2 in everywhere. And I've already done this math for you, make your life a little easier. So 64 times 2, 128. This next one will be 256 thirds. And the last one is plus 32. No, wait, hold on here. I'm missing somebody. There it is. 256 thirds, 128 fifths is what it is. So simplifying all that, be sure to multiply by your 2 pi. You should get that your volume is equal to 2,048 15ths pi. All right, next we're going to take a look at what the washer method is talking about. So washer method, looks like we have 2 radii. Let's talk about how that happens. So suppose I have, I'll just draw a curve here. Let's say this is some parabola. I could even have some linear function coming through here. And let's say I want to rotate around. I want to take this shape and I want to rotate around the x-axis. I'll switch colors here again for a second. So I want to take this representative rectangle and I want to rotate it all the way around the x-axis. If you notice, unlike the previous examples, when we had the disk method, there's no gap between the side of your region and the axis of revolution. What the washer method does is there's a gap here, all right? It creates a hole in here. So in this instance, my big R is the distance all the way up to what looked like I made a linear function. My little r is the distance to the curve, which sort of looked like a parabola. So the difference between these two is the height of it, but then I have to remember I have to rotate all the way around my axis. So when this rotates, I get what we call a disk shape. So grab my pen color again here. So this distance up to the top here, all the way up to the top here, this is my big R. And little r is the distance inside here. The smaller radius is little r. And so because there's a gap and it creates this hole, we call it a washer method. The shape they're calling a washer. You can think of it as a donut. So discs are M&Ms and washers are donuts, right? There's a hole in the middle. All right, so let's look at an example using the washer method. So it says, find the volume of the solid form by revolving the region from 0 to pi over 4, bounded by the y-axis, and the graphs of y equals cosine x and y equals sine x. Now, it doesn't tell us our axis of revolution. Hopefully it does in your notes. Let's see, does it have it? Yeah, and we're revolving it about the x-axis. So my slide doesn't show that. So again, I like to have a picture of what this looks like. So I have, I'll just draw This is 1 and -1. And this is, just make this pi over 2. All right, so first I'm going to draw my cosine graph, starts at 1. Right. And at pi over 2, it's 0. So this is cosine here. Should look sort of curved there. My sine graph starts at 0. So 0, 0, but then sine is 1 at pi over 2. So sine graph is here. So this region that we're looking at is the shaded region right here, and they intersect, if I draw this better, right here at pi over 4. So that's the region that we are rotating, and we're rotating, as you see in your notes, around the x-axis. So again, there's going to be a gap here between the shape and our axis of revolution. This is our shape here, a representative rectangle, and we're bringing that all the way down here. So if you notice there's a hole, there's a gap. So that's going to create that disc shape or that donut shape. All right, so let's talk about what big R and little r. Big R is going from the axis of revolution all the way up to the top curve. So our big R is our cosine function, the one that started at 1. Our little r is this radius going up from the curve or up from the axis to that lower curve. So our little r is sine x. So the volume that's going to be formed when we rotate this region about the x-axis is going to be pi times the integral from 0 to pi over 4, right? That's their point of intersection. That's where sine and cosine are equal to each other. Big R, which is cosine of x squared, minus little r, which is sine of x squared dx. All right, so I'm going to do a little simplifying here. So that's pi times the integral from 0 to pi over 4. And then we have cosine squared x minus sine squared x. Okay, now hopefully you recognize that that's a trig identity. If you don't recognize that, those are two that I highly recommend. This is the double angle identity for cosine. Before this class started this semester, I mentioned you should be sure to memorize your double angle identities for sine and cosine. This is the cosine identity. So another way I could write this is the integral from 0 to pi over 4. And instead of writing that as cosine squared x minus sine squared x, if I know my trig identities, I know that that's the same as the cosine of 2x, which is actually a lot easier to integrate. All right, you could integrate this way. It gets really messy because you're going to have, actually, I'm not sure you could. It'd be really gross. All right, so learn those double angles if you haven't. If this was a calculator question, no problem, but this isn't. And maybe they'd even throw it at you so that you know your identities. All right, so what I have to ask myself here then when I'm trying to integrate this is, was the chain rule done correctly? No, if the chain rule had done correctly, obviously the antiderivative of cosine is sine. So there should have been a 2 in here for doing the chain rule right. So remember, if you put that 2 in, you need to take a 1/2 out. All right, so now I have everything I need to find the antiderivative of this. I have a pi over 2 on the outside. Antiderivative of cosine 2x would be sine 2x. Remember that 2 is just there from the chain rule. So the antiderivative is sine 2x, and we are evaluating that from 0 to pi over 4. All right, so the first time I do it, I throw pi over 4 in there. 2 times pi over 4 is pi over 2. And the sine of pi over 2 is 1. So I have 1 minus, I put in 0, 2 times 0, 0, sine of 0, 0. And I end up with that the area between those two curves is, or not area, the volume of the area between those two curves rotated around the x-axis is pi over 2. All right, let's see our next one. All right, this time it says set up, but do not solve each of the following. This is pretty typical of what you'll see in the AP exam. You'll quite often get these set up problems. The reason why they don't give you the whole thing is, as you can see, they take lots of time and lots of steps. So often they will just give you the two curves, and you have to set up the integral. What they're looking for is, do you understand which curve is on top, which is on the bottom? Do you know how to find your limits of integration? Do you know what to do when your axis of revolution is something other than the x and y axis? So let's take a look at this first one. So example 4 says, set up but do not solve. Find the volume of the solid that results when the area bounded by y equals x squared and y equals 4x is revolved about the line y equals -2. So let me grab my pen here. All right, again, I like to have a picture. So just draw a little sketch. So I've got y equals x squared. And I've got the line y equals 4x, so y-intercept 0, slope is 4. So this is my shape. And I'm rotating it around the line y equals -2. So I'm going around this line. So notice there's a gap between my region that I'm rotating and my axis of revolution. So this is going to be a washer method. So I need to find my big R and my little r. All right, other things I'm going to have to know are my limits of integration. So I need to know, where does x squared equal 4x? Well, I can see that one of them is 0, right? I can see those two curves hit there. But I'll go ahead and do the math here. I'm going to bring the 4x over, set it equal to 0, factor out an x, and I get x minus 4. And so our limits of integration, I can set up my integral then. I have the volume is equal to pi times the integral from 0 to 4. And now I need to do my big R squared minus my little r squared. All right, well, one thing that's different about this is how far away from this axis of revolution. So if I look, and I'm going to grab my red here, from here to that line, right, that would be 4x. But I have to go all the way down to here. So one way I like to think about it is the top curve minus this axis of revolution. So I like to think of big R as being 4x minus -2. How did I get down there, right? That's my big R here. So 4x minus -2. Another way to think about it is, you know, from here to here is 4x. How much more are you going to get down to that horizontal line? You're going another 2. So you can also think of this as being 4x plus 2 more units, right? That's my big R. That's the furthest curve away from that axis of revolution. So I have 4x plus 2 squared. That's my big R, right? Minus, now I need to do my little r. Well, my little r is the parabola, so x squared. So little r, if you think about it, would go from here to here, would just be x squared, right? That's that distance. But now I have 2 more units added onto that. So little r is x squared minus a -2, or x squared plus 2 additional units, right? They would accept this either way, as 4x minus a -2 or x squared minus a -2. Either one of those answers is fine. You'll see it written either way on the exam. Right, this is kind of like the difference between the curve, right? Difference between the curve and the axis. It just happens to turn into addition. So I put that in here. That's my little r, so x squared plus 2 squared. the other thing they're going to look for is that you know all of that is together and you have your dx. All right, so when they're checking this, set up but do not solve, they're looking for, do you have your pi? Do you have the correct limits of integration? Do you know which curve is big R? Do you know which one is little r? Did you remember to put your squares in? Did you remember to include the fact that a washer is going to have this gap here between the curve and the axis of revolution? So they're going to look at that. All right, our next one this time says find the volume of the solid results when the area bound by y equals x squared and y equals 4x is revolved about the line x equals -2. All right, so we have not encountered one of these before. So this time x equals -2. This is a vertical axis of revolution. So when you see a vertical axis of revolution, you need to get everything written in terms of x equals. All right, so it's our same shape. So we still have that parabola. We still have y equals 4x. So it's still the same shape. But now our axis of revolution, let's switch colors here. Our axis of revolution is now x equals -2. This is now our axis of revolution. So I'm going to be going big R is going to be the distance all the way to the parabola this time. So that's going to be big R. And little r is going to be the distance from the axis of revolution to the linear function. That's going to be our little r. But before I can do those, I need to also know these limits of integration. And notice it's not going to be 0 and 4 anymore because we're looking at this sideways. You might even want to turn your head, right? This is still 0. But what's this point of intersection out here? Well, we know the x coordinate is 4. So if we plug that in here, 4 squared is 16, or you could plug it in here, 16. So our volume is going to be pi times the integral from 0 to 16. But now I have to write down big R and little r. Okay, notice we have to, because we have a vertical axis of revolution, we need to rewrite these. So we have y equals x squared, but I need to solve that for x. So I take the square root of both sides, and I get x is equal to plus or minus the square root of y. But if I look at what I'm considering in this curve here, I'm only looking at the positive half, right? So it's really x equals, I'm going to be using x equals the square root of y. And then this other curve, when I solve for x, I divide both sides by 4, and I get x is equal to 1/4 y. Okay, so all that's left is to figure out what that big R is. All right, so our big R, we know from here to here, that part of it is the square root of y, but now we've gone an additional 2 units here. So square root of y plus 2, or if you like to think of it as square root of y minus a -2. So that's big R then is going to be the square root of y minus a -2, or square root of y plus 2 squared, right? Remember, that's the one that's furthest away from your axis of revolution. That's your big R. Minus little r then is the 1/4 y. Right, and how far is that from the axis? Well, it's 1/4 y to here, plus another 2 units. We're going to square that. And the whole thing is not dx, it is dy. So that's our setup on that. All right, double check here. Pi 0 to 16. Yep. And you can also, one thing you should notice, I have these as inside the same parentheses. You will also get credit if you're to split these integrals. Same thing. You can have 0 to 16, and that should look like a nice integral. I can have my square root of y plus 2 squared dy, and now my pen is not cooperating, minus pi times the integral from 0 to 16 of 1/4 y plus 2 squared dy. Cool, they're like hieroglyphics. And those are squared. So either one of these answers is fine, all right? Whether you want to put them together or make them two separate. Probably if you're solving these, if you actually had to do it, separate might be a little bit easier. All right, so this is kind of a tough one. We will practice it. Don't worry if you don't get it right away. Take some time. Our homework assignment is homework 28 at AP Classroom. I included this picture. This is a really cool opera house in Kansas City. It is right across from the convention center where I have graded AP exams many times. It's now complete. You can actually go in there. It's really cool. But if you look, it's kind of this little volume of solids, a revolution idea, right? If your axis is going through here. So hope you enjoyed it. If you have any questions, you can email me or just ask me in class. All right, good luck.